All right, today we're going to tackle a huge question. How does AI find that one needle in a massive digital haystack? We're going to break down two really powerful but totally different ways of spotting something unusual. First, the geometric elegance of support vector machines, and then the brain-inspired smarts of neural networks. Let's get right into it.
Just think about cybersecurity for a second. Every single moment, you've got systems generating just mind-boggling amounts of data. Logins, network traffic, you name it. And almost all of it, like 99.99% of it, is totally normal. But hidden somewhere in that mountain of noise could be that one tiny data point that signals a massive security breach. So how on earth do you find it? And that is the core challenge of what we call anomaly detection. It's all about sifting through these mountains of what looks like identical data to find that one little thing that just doesn't belong. And this is absolutely critical, not just for security, but for everything from spotting fraud in finance to finding rare diseases in healthcare.
To solve this puzzle, we're going to look at two completely different ways of thinking. The first one is all about geometry. It finds patterns by, well, literally drawing lines and shapes in the data. The second approach is inspired by biology, trying to copy the amazing way our own brains learn to recognize what just doesn't fit in. So, first up, support vector machines, or what everyone just calls SVMs. At its heart, SVM is just a really clever geometric way to classify data. So let's dive into how it actually works. The core idea behind SVM is actually pretty simple, but it's super powerful. Imagine you've got two groups of dots on a chart, the normal, everyday activity and the suspicious stuff. Now, SVM doesn't just draw any old line to separate them. No, it tries to find the line that creates the absolute widest possible street or margin between the two groups. The wider that street is, the more confident the model can be. So that dividing line, it's got a fancy name, the hyperplane. And as you can see here, if your data is in 2 dimensions, the hyperplane is just a simple line. If you had 3 features to look at, it'd be a flat plane. And in even higher dimensions, the kind we can't even picture, it's what mathematicians call a flat subspace. But the idea is the same. It's the decision boundary. Okay, so let's break down a few key terms here. That street we keep talking about, its width is called the margin. Simple enough. Now, the data points that are right on the edge of that street, the ones closest to the line, those are the most important ones. They're called support vectors because they literally support where that hyperplane ends up. And the whole goal, the whole game, is to find the widest margin possible. That's why SVM is known as a maximal margin classifier. Okay, that all sounds great, in a perfect world where data is neat and tidy. But we all know real-world data is messy. It's noisy, you've got outliers, you've got data points that just refuse to play by the rules. So what happens when you just can't draw a perfect line? And this is where the idea of a soft margin becomes so important. A hard margin classifier is a total perfectionist. It insists on separating everything perfectly. The problem is that makes it super sensitive to even a single outlier. A soft margin classifier is way more practical. It says, look, let's find the best possible street we can, even if it means we have to let 1 or 2 points be on the wrong side. That flexibility is what makes it work in the real world. All right, so that's how SVM is great at separating 2 different groups. But wait, how does that help us find that one needle in the haystack, right? We're not trying to separate 2 groups. We're trying to find one weirdo. Well, let's look at a special version made just for that. This is where something called One-Class SVM comes in, and it's a really cool twist on the idea. Instead of drawing a street between 2 classes, it learns how to draw a boundary around the one single normal class. Think of it like building a fence around the entire neighborhood of normal data. Then anything that falls outside that fence gets flagged as a weirdo, an anomaly. Now, for this to work, the model kind of needs a hint from you. You give it this hint with a setting called new. And new is basically just your best guess for the percentage of outliers in your data. Are you hunting for super rare events, like 1 in a million? Or do you kind of expect about 5% of your data to be a bit strange? Setting new just helps the model build that fence with the right amount of sensitivity. So SVM is really powerful, but it's all about finding these geometric boundaries, even if they're complex, curvy ones. But what happens when the patterns that define an anomaly are just too intricate, too tangled up for even a clever geometric shape to capture? Well, for that, we need to turn to our second approach, artificial neural networks. This is an idea that's directly inspired by that massively interconnected web of neurons that we all have sitting inside our own skulls. Okay, so the most basic building block of any neural network is something called the perceptron.
It's the simplest version you can imagine. Just a single artificial neuron. It takes in a bunch of inputs, it multiplies each one by a weight to decide how important it is, adds them all up, and then uses a simple rule to decide whether to fire off a 1 or a 0. It's basically a tiny little decision maker. And you know what? This tiny little thing is actually surprisingly capable. A single perceptron can solve any problem that is linearly separable, which is a fancy way of saying you can solve it by drawing one single straight line to separate the yeses from the nos. This includes basic logic problems like and or. So if one little neuron is that smart, why do we always hear about these massive networks with millions of them? Well, it turns out that this simple, elegant model has a very famous Achilles heel. You know, back in the day, researchers were so excited about the perceptron. They thought they'd cracked the code to intelligence. But then, they hit a brick wall. There was a surprisingly simple little problem that it just could not solve no matter what. And this is the culprit, the XOR or exclusive OR problem. Just look at the data. Go ahead, try to draw one single straight line that separates the blue dots from the orange ones. You can't do it. It's impossible. And since a single perceptron can only draw one straight line, it's completely powerless here. This discovery was actually a huge deal. It was so discouraging, it helped trigger what people call the first AI winter, slowing down research for years. So what was the solution? Teamwork. A multi-layer perceptron is a network that has one or more hidden layers of these neurons stacked between the input and the output. By having these extra layers, the network can learn to combine their simple little straight lines to form complex, squiggly, nonlinear boundaries. This team of neurons can solve the XOR problem easy peasy and a whole lot more. Okay, so when you're training these networks, there's another really important knob you have to tune, the learning rate. This basically controls how big of a step the model takes when it's adjusting its weights to fix an error. And as you can see here, it's a total trade-off. If you set the learning rate too high, it learns fast, but you risk just flying right past the best solution. If you set it too low, it's much more careful, but it can take forever to train and might get stuck. Finding that Goldilocks zone is a huge part of training these models. All right, so we've gone down two totally different paths to hunt for the same thing, right? One draws these elegant boundaries in data, and the other one builds this complicated computational brain. Let's put them side by side one last time. So let's just recap. On one side, you've got SVM's geometric approach. It's all about finding that widest possible street for a really clear separation. It's elegant, it's mathematically sound, and it's perfect for when your data has a pretty clear structure. On the other side, you've got neural networks and their computational approach. They use these layers of neurons to learn incredibly complex, subtle patterns that geometry alone would probably miss. They're super flexible and can model almost anything. And that really leaves us with one big question for the future. In this ongoing hunt for digital threats, both of these methods are absolutely critical. SVM gives us a robust geometric solution, while neural networks offer this almost unlimited flexibility. But as our digital world just gets more and more complex, which philosophy do you think will ultimately prove more important? The clean elegance of geometry or the messy, adaptive power of biology?